Every day, more than 100,000 commercial flights take off across the globe. Passengers board, stow their luggage, and settle in largely unaware of the extraordinary engineering beneath their feet. At cruising altitude, the outside air temperature drops to -60 degrees Celsius. The aircraft moves at nearly 900 kilometers per hour. And at the heart of each engine, combustion gases reach temperatures exceeding 1,500 degrees Celsius, surpassing the surface temperature of certain stars. The question engineers have wrestled with for decades is deceptively simple: how does metal survive conditions like that? The answer lies in a group of 17 elements that most people have never encountered, elements with names like yttrium, neodymium, dysprosium, and lanthanum. They are called rare earth elements. And without them, modern aviation would not exist. What are rare earth elements? Rare earth elements, commonly abbreviated as RES, comprise 17 metallic elements. 15 belong to the lanthanide series on the periodic table. 2 additional elements, scandium and yttrium, are grouped with them because they share similar chemical behaviors and are typically found in the same mineral deposits. The name is, in a sense, misleading. Cerium, one of the most widely used RES in industry, is more abundant in the Earth's crust than copper. Even thulium, the least common of the group, is more plentiful than gold. They are called rare not because of scarcity, but because of distribution. These elements are almost never found in economically viable concentrations. They are dispersed in minute quantities across broad geological formations, making extraction and refinement technically demanding and commercially expensive. An analogy: imagine dissolving a teaspoon of salt into an Olympic swimming pool. The salt is present. Recovering it in pure form is another matter entirely. What makes RES industrially irreplaceable is their combination of magnetic, thermal, optical, and catalytic properties that no substitutes can fully replicate. In materials science, they are sometimes called the vitamins of industry, needed in small quantities, yet essential to function. In aviation specifically, their role is pervasive, from the turbine at the core of the engine to the electrical systems running throughout the airframe. The jet engine, operating beyond its own limits. To appreciate why rare earths are so critical, one must first understand the operating environment of a modern turbofan engine. Engines such as those powering the Boeing 787 Dreamliner or the Airbus A350 operate on a straightforward thermodynamic principle: draw in air, compress it, combust it with fuel, and extract energy from the resulting gas flow as it expands through a series of turbine stages. The turbine blades at the heart of this process sit directly in the path of combustion gases reaching between 1,500 and 1,700 degrees Celsius. Here is the problem: the nickel-based superalloys from which those blades are forged have a melting point of approximately 1,300 degrees Celsius. The engine, in other words, runs hotter than the melting point of its own components. This is not a design flaw. It is an engineering challenge that rare earth elements and the materials they enable have been specifically developed to solve. Yttrium, the thermal barrier. Yttrium element 39 is arguably the most consequential rare earth element in jet aviation. Turbine blades in modern engines are coated with a ceramic layer called a thermal barrier coating, or TBC. The most widely used formulation is yttria-stabilized zirconia YSZ, a compound in which yttrium oxide is added to zirconium oxide. Zirconia on its own is an excellent thermal insulator but is structurally unstable at elevated temperatures. It undergoes phase transformations, expands unevenly, and fractures under thermal cycling. Yttrium arrests this instability by locking the zirconia into a tetragonal crystal phase, preventing the destructive phase changes that would otherwise occur. The result is a ceramic coating typically between 100 and 300 micrometers thick that insulates the underlying metal blade, reducing its surface temperature by as much as 150 to 200 degrees Celsius relative to the gas stream. This margin is what makes modern high-efficiency engines thermodynamically possible. An advancement worth noting: Recent research has focused on next-generation TBC formulations using rare earth zirconate and hafnate compounds, materials capable of operating beyond the practical temperature ceiling of conventional YSZ. These emerging coatings promise a further improvement in thermal efficiency, directly translating to reduced fuel consumption and lower emissions across the global fleet. Without yttrium-based thermal barrier coatings, engine operating temperatures would be substantially lower, fuel efficiency would decline, and routes such as Singapore to New York, currently among the longest non-stop commercial flights in the world, would require an intermediate stop. Neodymium and dysprosium, the magnet revolution. Aviation's ongoing shift toward what engineers call the more electric aircraft architecture, replacing hydraulic and pneumatic systems with electrical equivalents, has made permanent magnets a central component of modern airframes. The dominant technology is the neodymium iron boron magnet, developed in 1982. NdFeB magnets are the most powerful class of permanent magnet yet produced, generating magnetic fields far stronger than their predecessors at a fraction of the size and weight. In a modern commercial aircraft, these magnets are found in electric actuators controlling flight surfaces, onboard electrical generators, fuel and hydraulic pumps, environmental control systems, avionics, cooling, and landing gear mechanisms. The Boeing 787 generates 1.45 megawatts of onboard electrical power, the highest of any commercial aircraft at its time of introduction. That generating capacity is underpinned by neodymium magnet technology. However, neodymium magnets have a significant operational vulnerability: they lose magnetic strength as temperature rises. This phenomenon, known as coercivity reduction, is a serious concern in aircraft, where temperatures can range from -60 degrees Celsius at altitude to well above 150 degrees Celsius near engine nacelles and avionics bays. Dysprosium element 66 addresses this directly. When added to neodymium magnets in concentrations of 2 to 6%, dysprosium significantly raises the coercivity of the magnet, maintaining field strength across the wide temperature range experienced in service. A critical supply dimension, dysprosium is among the scarcest of the commercially significant rare earth elements, produced almost exclusively as a byproduct of other remining operations. Its supply is structurally constrained, and demand is growing as electrification of aviation and transportation broadly accelerates. This has focused considerable research effort on dysprosium lean and dysprosium-free magnet formulations, though no commercial alternative has yet matched the performance of the established alloy at operating temperatures. Lanthanum and cerium, strengthening the alloys. Beyond coatings and magnets, rare earth elements are incorporated directly into the metallic alloys that form the structural foundation of jet engines and airframes. Lanthanum, the first element of the lanthanide series, is added to nickel-based superalloys in trace concentrations during manufacture. Its effect operates at the microstructural level. Lanthanum refines the grain size of the metal as it solidifies, producing a finer, more uniform internal architecture. Finer grain structures improve tensile strength, fatigue resistance, and crack propagation behavior, all of which translate directly to extended component service life and longer maintenance intervals. Cerium serves a complementary function in aluminium alloys, which are used extensively throughout airframe structures. At elevated temperatures, conventional aluminium alloys are susceptible to microstructural coarsening, a process by which the internal phases of the metal consolidate and degrade mechanical properties. Cerium additions form thermally stable intermetallic phases that resist this coarsening, preserving strength and oxidation resistance through repeated thermal cycles. An emerging application: researchers at several national laboratories and aerospace manufacturers have recently demonstrated cerium-modified aluminium alloys capable of retaining their mechanical properties at temperatures significantly above the operational limit of standard aerospace aluminium. If this technology matures to production readiness, it could enable structural weight reductions across large airframe sections, with meaningful implications for fuel efficiency and emissions. In an industry where a single kilogram of excess weight costs an airline thousands of dollars in fuel annually across its fleet, the compounded value of rare earth enhanced materials is measured in the billions. The broader ecosystem in aviation. Several additional rare earth elements contribute to aviation in more specialized roles. Praseodymium, element 59, is combined with neodymium in magnet formulations to balance cost and performance. It also imparts specific optical properties to glass coatings used in cockpit windows, where spectral filtering and glare reduction are operationally significant. Samarium, element 62, forms samarium cobalt magnets, the predecessor technology to NdFeB. While delivering lower magnetic energy density overall, samarium cobalt magnets exhibit superior thermal stability, making them the preferred choice for sensors and actuators mounted in close proximity to engine hot sections where temperatures exceed the operating range of neodymium-based designs. Terbium, element 65, is used in magnetostrictive materials, substances that undergo controlled dimensional changes in response to a magnetic field. In precision actuators and vibration damping systems, this property enables active structural control, reducing fatigue loading on critical components. Gadolinium, element 64, with its exceptional neutron absorption cross-section, is under active investigation for use in radiation shielding composites relevant to high-altitude flight, where galactic cosmic radiation exposure is a recognized occupational health consideration for flight crew. Europium and ytterbium contribute to the phosphorescent and display coatings used in instrument panels and cabin systems, where their precise luminescent properties underpin readability and reliability across a wide range of ambient light conditions. The geopolitical dimension. The dependency of global aviation on rare earth elements raises a strategic question that extends well beyond procurement management. According to the International Energy Agency, China accounts for approximately 60% of global rare earth mining output and controls more than 85% of global processing and refined magnet manufacturing capacity. The concentration of this capacity in a single nation represents a structural vulnerability across the entire aerospace sector, civil and military alike. The consequences of this dependency have moved from theoretical to operational. In September 2022, the United States Department of Defense was compelled to suspend deliveries of the F-35 Lightning II fighter aircraft after the discovery that an alloy used in a component of its engine contained a combination of cobalt and samarium originating from Chinese-controlled supply chains in violation of domestic defense procurement regulations. Each F-35 airframe contains approximately 417 kilograms of rare earth materials distributed across its propulsion, avionics, targeting, and electronic warfare systems. The incident was not an anomaly. It was a signal. Commercial aerospace faces the same exposure. Every major engine manufacturer, GE Aviation, Rolls-Royce, Safran, and Pratt & Whitney, sources rare earth inputs through supply chains that route, at some stage, through Chinese processing facilities. In a scenario of significant export restriction, production timelines and maintenance supply chains for commercial aircraft would be materially disrupted. China has demonstrated its willingness to use rare earth access as a lever in trade disputes. In 2010, it imposed export restrictions that sent global rare earth prices to multiples of their prior levels. Whether a more comprehensive restriction would be deployed in a future geopolitical context is an open question, but the structural dependency makes the answer consequential. Strategic responses and the path forward. The aerospace industry and the governments that underwrite it have not been passive in the face of this risk. Supply diversification has become a policy priority across multiple jurisdictions. The Mountain Pass mine in California, the only significant rare earth mining operation in the United States, has been recommissioned and is scaling production. Australia's Lynas Rare Earths operates the only major rare earth separation facility outside China, with capacity expansions underway. Canada, India, and several European nations are investing in domestic extraction and refining infrastructure. Material innovation is running in parallel. Engineers at GE Aerospace, Rolls-Royce, and academic institutions are developing thermal barrier coating chemistries based on rare earth zirconate and hafnate compounds, materials that can operate at temperatures exceeding the practical ceiling of current yttria-stabilized zirconia while potentially using smaller quantities of scarce heavy rare earth elements. Magnet research is pursuing two parallel tracks. One focuses on further optimizing NdFeB formulations to reduce dysprosium content without sacrificing high-temperature performance. The other investigates fundamentally different motor architectures, switched reluctance and wound field synchronous designs that eliminate the dependency on rare earth permanent magnets entirely. NASA, Airbus, and a number of well-funded startups are active in this space, though none has yet demonstrated the power-to-weight performance required for primary propulsion applications. Recycling and circular economy approaches represent a longer-term lever. Rare earth elements can, in principle, be recovered from end-of-life magnets, coatings, and alloy components. At present, recovery rates are low due to the technical complexity of separation and the economics of primary mining. As primary supply tightens and material values increase, the case for closed-loop recovery in the aerospace sector is strengthening. The next time you observe a contrail tracing its arc across the sky, consider what sustains that line. Inside each engine, temperatures exceed the melting point of the metal from which the components are made. Forces that would fragment ordinary alloys are contained by materials engineered at the atomic level. Ceramic coatings a fraction of a millimeter thick, magnets smaller than your fist, trace additions to alloys measured in parts per million. Yttrium, holding the thermal barrier in place on a turbine blade spinning at thousands of revolutions per minute. Neodymium, generating the magnetic fields that power every electrical system aboard. Dysprosium, preserving that magnetism as temperatures swing by hundreds of degrees through each flight cycle. Lanthanum and cerium, silently strengthening the grain boundaries in metal that must last for tens of thousands of flight hours. These are not exotic or peripheral materials. They are the foundational layer on which modern aviation rests, mined from the earth, refined through complex chemistry, and engineered into components so precise they must be measured with instruments that did not exist a generation ago. The supply chains are fragile. The geopolitics are shifting. The research community is working with genuine urgency. And above it all, every day, 100,000 flights take off.